Moving on to the next session, we have Professor S.K. Neogy and Professor T.E.S. Raghavan. S.K. Neogy is a professor and head of Indian Statistical Institute, Delhi Center, India. He will be delivering talk on characterization of special matrix classes using degree theory. One more speaker, T.E.S. Raghavan, is an emeritus professor at Department of Mathematics, Statistics and Computer Science, University of Illinois, Chicago. He will be speaking on linear complementarity via zero-sum matrix games. May I now request Professor T.S.S. R.K. Rao to chair the session. Over to you, sir.
Thank you very much. It's my pleasure to invite these distinguished colleagues to give talks in this session. So may I request Professor S.K. Neogy, who is also head of the Indian Statistical Institute at Delhi, to give his presentation. I'm not getting the audio.
So I'm glad that I'm able to give a talk in the honor of Professor C.R. Rao. The title of my talk is Characterization of Special Matrix Classes Using Degree Theory. So I'm from Indian Statistical Institute, Delhi. So let me give first outline of the talk. So I start with give some preliminaries, and then I'll introduce some concept degree of a LCP map, linear complementarity problem map. And then I'll talk about Stewart extension formula of degree, and then I'll talk about different matrices of degree plus minus 1, and then I'll talk about superplus matrices. So let me start with the preliminaries. The linear complementarity problem, it started with a paper of Duhal, and that time that name was different. It came with a name as a problem of linear inequalities. And subsequently, that with the thesis of Cottle, this particular subject took off, and over 5 decades, host of researchers have worked on this problem, and so that I am going to elaborate and what are the developments, and something that finally that I want to say that degree theory plays a big role of characterizing the matrix classes associated with linear complementarity problem, and what are the other developments has happened with respect to these classes and degree theory that I am going to explain. So let me tell you that linear complementarity problem, it is basically to find x such that given a vector a and q, Ax plus Q greater than equal to 0, and X transpose Ax plus Q is equal to 0. X transpose Ax plus Q is equal to 0. This is the complementarity constant. Other one is the feasibility condition that which is given by the linear inequalities. I will make use of the term pos A, that is the convex cone generated by the matrix A. So that is basically that set of all x such that y greater than equal to 0 and x is equal to ay. K is the set for all q for which SQA is not equal to phi, that is the solution set is non-empty. And CA is the union of strongly degenerate complementary cones of A, and K, the set of all vectors in Rn which are non-degenerate with respect to A. And in this connection, the two matrix classes Q and Q0 arises. The class Q is basically that for all Q, if solution set QA is not equal to phi, that is, if it is non-empty, then we say that it is a Q matrix, and a matrix is said to be a Q0 matrix if a feasible solution implies, and it will be the solution of the LCP. That is, FQA not equal to phi implies SQA not equal to phi. So in this context, I'll make use of the complementary cones. Given a matrix A and a set alpha, which is a subset of 1 to n, will denote CA alpha as complementary matrix with respect to A. Complementary matrix of A with respect to alpha, and we will denote CA alpha dot J is minus A dot J if J belongs to alpha, and CA alpha dot J is equal to I dot J if J doesn't belong to alpha. And the associated cone, cos of C alpha, is called the complementary cone relative to A. So these concepts we need it subsequently. If determinant of C alpha not equal to 0, then it is set to a complementary basis, and the cone, complementary cone with respect to alpha, is said to be non-degenerate if delta alpha is not equal to 0. Otherwise, it is said to be a degenerate complementary cone. A degenerate cone post CA alpha is said to be strongly degenerate if there exists 0 not equal to x belonging to Rn plus such that CA alpha x is equal to 0. Now, given a matrix A and alpha, the matrix A is said to be non-degenerate if delta alpha alpha is not equal to 0 for all alpha belong a subset of 1 to n. And any solution of LCB QA is said to be non-degenerate if W plus Z is greater than 0. Otherwise, we will say it is a degenerate solution. And when that every solution is non-degenerate, then a vector Q is said to be non-degenerate with respect to A. We'll also need this terminology. A set is connected if there do not exist disjoint open sets U and V, such that U intersection C is not equal to phi and V intersection C is not equal to phi, and C is contained in U union V. Now, for any set S contained in Rn and any x belonging to S, the connected component of a set S containing S is defined as the union of all connected sets C such that X belongs to C containing S. As I said, that so what are the problems that associated with the linear complementarity problem? As it is known that linear complementarity problem, it unifies a large number of optimization problems like linear programming, convex quadratic programming, linear fractional programming, biometric games, etc. So definitely a large number of researchers was interested to study linear complementarity problem. And so the basic question which arises, what is the class of matrices M for which LCB QM has a unique solution for all vectors Q? So you might have seen that this question is very much relevant, and so that answer is known, partially known about this, and about the next question: what is the class of matrices for which LCB QM has a solution for all vectors Q? This class is denoted by Q, and its elements are Q matrices. Now, An ideal answer will be to provide a set of necessary and sufficient conditions which could be used to check in finite time. And if any, given matrix M belongs to that class. Okay. So that is about the first one. In case of question 2, that some partial but not entirely satisfactory answers are available. Now we are going to talk about these classes, and so before that, I would like to say some more open problems which are there. That if we ask in terms of complementary cone, question 2 is asking the class of matrices for which the complementary range of M equals to Rn. Okay. Now note that for an arbitrary matrix M, the cone Km is generally not even convex and much less equal to Rn. Okay, so we can at least ask for the class of matrices M for which Km is convex. Now this matter is closely related to what is the class of matrices M for which LCB QM is solvable whenever it is feasible. I have mentioned this class is known as Q0, and the matrices which has this which belongs to those class, that those are called Q0 matrices. Now the open problem associated with this that provide a set of necessary and sufficient conditions which could be used to check in finite time if any matrix M belongs to class Q and Q. So therefore, so we have two problems in hand, that that uniqueness of the solutions and the existence of the solutions. So these are the two problems in hand, and so here one more concept in the literature which plays an important role, that is called principal pivot transform. Now principal pivot transform of A with respect to some set alpha is defined as follows. So here M is defined like this, that if M is the principal pivot transform of A, we can write M alpha alpha and M alpha alpha bar, M alpha bar alpha like this. And when you take a PPT, this principal pivot transform of A with respect to alpha, alpha, that obtaining the pivot on A alpha alpha, then you get LCB, you know, that as Q prime M, and where Q alpha alpha is like this, you will have this one. And here interesting thing is that that cardinality of the solution set will remain same. Okay. Note that PPT is defined with respect to dose alpha for which state alpha alpha is not equal to 0. Now we try to characterize some of the matrices that using degree theory. Now let me tell you that what is the degree of an LCB map. Suppose f is a piecewise affine function of the form fz given by this, and where this denotes that component wise minimum, and fa is, which is from Rn to Rn, be a piecewise linear map, and which I write it down as fax, which is equal to x plus minus ax minus, where xi plus will denote max of 0 xi, and xi minus is 0 minus xi. And note that we can write for any x belonging to Rn, x is equal to x plus minus x minus. Now, if you see that an LCB QA is equivalent to finding x belonging to Rn such that this fax is equal to, and if x belongs to the interior of an orthant Rn and data alpha alpha is not equal to 0, so here alpha is set of all I for which xi less than 0. So the index of alpha, you can write it like this. Okay. Say this is equal to sine of a data alpha alpha, data alpha alpha is this. Now so if Q and Q belong to Rn minus Ka and lie in the same connected component, then degree of A Q is equal to degree of A Q prime. And when Rn minus Ca is made of a single connected component, so what will happen? Then we can say that the degree of A at Q is defined and equal at the same constant for every Q belonging to R. And such a scalar, we will call it as degree of A, and we will denote it by degree of A, DEG in the bracket A. And local and global degrees of an LCP map are quite useful in identifying the subclass of Q and Q0. They mentioned that we want to get a characterization of Q and Q0 matrices using degree theory, and we're going to talk about that some of the well-known characterizations are given a newer perspective in terms of degree theory. Now, let us compute that suppose we have a 2 by 2 matrix. A is like this, and you can draw the complementary cones. In the beginning, I have discussed what are these complementary cones, and we can easily see that R square is made of a single connected component. Okay, and if you draw the complementary cones, you will see that it is a single connected component, and so therefore, in view of the discussion done earlier, that the degree of A is well defined, and it is easy to check. For every vector Q greater than 0, we have exactly 3 solutions. Okay. And as we mentioned that if we add the respective determinantal signs and then we can get the degree, it will be -1. Now, when we talk about degree of an LCP map, that there obviously that one matrix class comes into picture, that is the R0 class. So R0 class, a matrix is said to be in R0 class if LCP 0A has a unique solution, W is equal to 0, Z is equal to 0. It has a unique solution, Z is 0, so it has only trivial solution. Okay. So if A belongs to R0 and Rn is a single connected component, and degree is well defined, and if degree of A is not equal to 0, then A belongs to Q. So this is a known result. An interesting property is that it is carried over principal pivot transform. Okay, so if let A belongs to R0 and degree of A is R, then all its PPT degree remains same. Okay. Degree of M belongs to R. The degree of M is equal to plus minus R. It is same. So here that let us consider a matrix that you can see that A has 2 principal minors, which is equal to 0. These are the principal minors, which is equal to 0. And so one can check that LCP 0A has a unique solution Z equal to 0. So you can see here that 0A has a unique solution, and so therefore A is an R0 matrix. And for a Q greater than 0, you will see that LCP QA has a unique solution. Okay. So therefore, degree of A is equal to 1 and A is a Q matrix. Okay. So this is a nice characterization that in the previous page which I mentioned, that if A belongs to R0 and Rn is a single connected component, then I can say that degree A not equal to 0 and A belongs to Q. So otherwise it is very difficult to figure out whether a matrix is Q matrix or not. There's no satisfactory way to check whether a matrix is a Q matrix or not. So for a vector K, non-degenerate with respect to A, we define the number degree A as sine of det A alpha alpha. So where the summation is defined over all index set alpha. such that Q belongs to pos of C alpha. So sign of x is 1 if x is a positive real number, -1 if x is a negative real number, and 0 if x is equal to 0. And this expression star is same for all Q non-degenerate with respect to A and is called the degree of A. And the term inside the summation sign in star are known as indices of A. So Stewart extension, now I'm going to discuss that Stewart extension formula of degree. So in our definition of degree of an LCP map, we made use Q belongs to Rn, which is non-degenerate. The new formula of Stewart extend this definition to vectors that are semi-non-degenerate with respect to. And Goda stated a neater form of this formula and made use of the following result. The number of solutions for certain class of linear complementary problems. So we'll now define, we mean by a vector being semi-non-degenerate. Let Z be a solution of LCP QM, and for this Z, let us define the following index set. And so this is the Sood complement. And so when alpha is empty, then MSS alpha is equal to M gamma gamma when gamma is empty. And MS alpha alpha is the identity matrix of an appropriate order. The solution Z is called semi-non-degenerate if the corresponding principal submatrix M alpha is non-singular, where alpha is defined as above is non-singular. So a vector Q belongs to Rn is non-degenerate with respect to M if every solution of LCP QM is semi-non-degenerate. And for a non-degenerate matrix, every Q belonging to Rn is semi-non-degenerate with respect to M. Now Stewart's extension formula of degree M for any Q, any Q belonging to Rn semi-non-degenerate with respect to M can be stated as that this is the formula. Degree of M is summation of sign determinant of M alpha alpha and degree of MS alpha alpha, where the summation is defined over all index set alpha and Q belongs to pos C alpha. And indeed, if M is a non-degenerate matrix, then the above definition of degree is valid for any Q belonging to Rn, and sign of x is 1, that if x is a positive real number, and -1 if x is a negative real number, and 0 if x is equal to 0. So this Stewart formula, that extension formula, this is very useful to figure out the degree. So that is illustrated in this example. So yeah, let us consider this matrix, and it is easily seen that no principal minor that it has no principal minor 0 and LCP I dot 1, that is 1 0 0. This has that A and the given matrix A. This has the unique solution W is equal to I dot 1, Z is equal to 0. Now, if you make use of the Stewart extension formula for Q is equal to I dot 1, then degree of A may be found as the same as that principal submatrix of A, leaving the first row and first column. And you can see that if you look at the first row and first column. So this is -1, 2, and 1, -1. And you have seen in the previous example, no, that so here degree of A is -1. So it follows that degree of A is -1. Now we are going to discuss the matrices of degree plus minus 1. As all of you know that a P matrix in the context of LCP, that is very important, because that if A is a P matrix, then LCP QA has a unique solution for all Q belonging to Rn. And it is defined as that a matrix is said to be P or P naught matrix if all its principal minors are positive or non-negative. And even as I said that even the definition, if you look at the definition, that it is just for checking the principal minus positive or negative, but there's no satisfactory way that you can find out how to check a matrix is P or P naught. It is still unsolved. There's no satisfactory algorithm for this. In fact, that in the beginning, that maybe that 20, 25 years back, Murthy tried to look at this problem. So he tried to give a some characterizations which ultimately can lead to a problem of checking the matrix, the 2n plus 1 vectors. The checking that to conclude that whether matrix is P or P naught, but it doesn't work for the higher degree, and there are some counter examples out there. Then after that, not much work has been done in this direction. So it's still that open, and if the degree of A1, whenever A is a P matrix, then degree of A is always 1, and a P matrix is also a Q matrix. A is called the N or N naught matrix if all its principal minors are negative, or N naught if it is non-positive. The N and N naught matrix, this is also a well-studied matrix in the literature over the years, and a lot of researchers have worked on this class of matrices. In fact, if you look at LCP, there are more than 50 matrix classes out there in a paper by Cottle, and all these matrix classes are of great importance in the sense they have nice structures, and that with respect to solution of LCP, there are nice characterizations are there, and still there are lots of problems which needs to be studied with respect to those matrix classes. That to the matrix theoretic researchers, maybe that P naught and N naught, these matrix classes are well known. But apart from that, that large number of matrix classes which arises in the context of LCP, that's many are not well studied. So therefore, a matrix is called N or N naught matrix. Then when A is the N matrix, then degree of A is either 0 or -1. We denote K is the set of all vectors in Rn which are non-degenerate with respect to A, and for a matrix to belongs to class Q, it suffices to observe that for any Q belonging to Rn minus QA, LCP has a solution. So in this context, that the degree that one matrix class, which is called superfluous matrices, that has come up, and A is called a superfluous matrix if LCP QA has at least K plus 1 solutions for every Q belong to Rn minus Ka, given that degree of A is equal to K. And for any integer K, there exists an R naught matrix of degree K, then there exists a superfluous matrix of degree K. And there's an observation that however about Q matrix is that this is the Q matrix, this is given by Howe, and it is shown that A is non-degenerate, and Howe proved that degree of A is 0. And, so therefore, it was Howe who first showed that with A that there exists a 0 degree Q matrix. This particular that studying various matrix classes using degree theory, there are lots of problems which are open, and there is a lot of scope is there to study the variety of matrix classes which arises in linear complementarity problem using degree theory. Thank you. These
Thank
are
you,
the
Professor
references
Neogy.
that one can look at. I will say that these are partial list. You can see the references there.
Thank you again. We may have time for just one or two questions.